From DataStax, this is the Distributed Data Show podcast. Well, hello everybody, and welcome again to this next episode of Graph Code with Denise and David. And as usual, I am David Jones-Gilardi, joined by I want to say illustrious every time, but
I appreciate that.
I don't know. I guess I'll go for the illustrious Denise Gosnell. I'll tell you right now, if Patrick is watching this, Patrick is going to totally school me on my use of the word illustrious. But anyway, hello, Denise.
It's good to see you, David, and everyone. Hello, my name is Denise. I'm very, very grateful to be here. I absolutely love this part of our Tuesdays. It's my favorite.
Yeah, I agree. This is a good hour to have. And I see, oh yeah, we're getting, okay, by the way, for those of you who are on LinkedIn, we are actually watching you today.
This time, yes. I'm so sorry that we missed all those comments. It was great.
You had all sorts of interaction. People were asking questions and we just totally ignored you. And what's cool about LinkedIn that I did not realize, Denise, is that folks can react with thumbs up and hearts and all sorts of things. And when we started, we got some love. So thank you for the love. We really appreciate that. We are watching this time. I see some folks there. All right. So Denise.
Actually, so to that point, what I do have pulled up here on my phone were all of the questions from last week on LinkedIn that we did not get to.
Oh, all right. Let's do it.
So we had 28 questions there. I'm not going to go through all 28 because there's a few that were duplicates.
Let's take the hour to answer the questions and get into the next part.
Yeah. So absolutely keep asking lots of questions. We're here for you and your questions. We've got it all pulled up. I appreciate it. So thanks for all that. I absolutely love all the extra support for the O of N analysis chapter on GitHub. I think for those of you who have worked on projects for multiple years, I went through the bowels of all of my files and folders over here. That was hard to find. So I have a request out to O'Reilly because it's in a feature branch on a really old draft of the book. So I'm still digging, but please be patient because it's going to be a deep sleuth to find that one. All of these sessions are available online. So for those of you who are just kind of hopping in for this, for this one, you can go to our YouTube channel or any of our social channels. And you can find all of the historical episodes, right, David?
Yes. As a matter of fact, if you go to DataStax developers, I should probably have that link available. Let me go ahead and grab it real quick. Here it is. If for the YouTube folks, you're already there, but if you're on LinkedIn, I will go ahead and post that link. That link that I just dropped into LinkedIn will bring you directly to this video, but through that, you can see the DataStax developers channel. If you would, go and click subscribe, right? I realize that's the shameless plug for these things, but we have not just these videos, but all sorts of our other videos. All of our content's free and everything. A ton of information on Apache Cassandra, obviously things like Graph. You get to see some of the other things we're up to. So again, that's DataStax developers channel. I just dropped that in LinkedIn. And for those of you on YouTube, you're already watching. So if you're watching this on YouTube and you haven't subscribed, please subscribe.
That's great. Yep. So thank you for that. There's a ton of questions from last week on LinkedIn. Like I said, we had 28 questions there. So thank you guys so much for all the questions. A lot were just about recordings and accessibility. And an excellent question that we didn't get to last week, but we went ahead and just designed today all around that question. It was wondering, is there a trace on how many underlying Cassandra partitions are involved in your gremlin query? So short answer to that is yes. You can use .profile or .examine at the very end of your gremlin query. And that is going to give you a full trace of all of the information and profile statistics of your query that you might want. You can also then use, you also can deep dive into the actual Cassandra queries that we're running under the hood if you're curious. So if you're out there and you're wanting the fast answer because you're going to just go code and break, you're awesome. .profile or .explain, and you'll get that full stack trace that you can understand how many partitions are being crossed.
Cool.
Today, though, we are going to dive deeply into understanding how many partitions are involved in graph structured data. So I think, David, we had a few things planned, right? We're going to start with mapping distributed adjacency lists into Cassandra to kind of see how Cassandra has a native graph data structure in it. Mm-hmm. We're going to start there. After that, we're going to be doing data loading. Is that correct?
Yes. I definitely did a little of the homework. So Denise, if you've been watching these, you'll know that every week Denise gives me just a little bit of homework. Now, the homework, to be clear, is just, I'm going to explain to you what I've done and how you can go through it and do it yourself. This is also all explained in the GitHub repository, the Graph Dash book GitHub repository as well. I've just done a little bit of upfront work, so it's a little smoother when we come on here, so we can spend more time in the actual traversals and walking through it as compared to having you all watch me, like kind of fat finger my way through command terminal and such. So anyway, so I will explain that. Yeah, I'm going to have to anyway. But yeah, we will go through a little bit, but it's not too much. It's just some of the data loading pieces and using DS bulk to load data into our graph schema.
Yep. And to the gentleman who asked the question about understanding number of partitions, we even have another super sweet trick to show you guys, and that's called index 4.
Yes.
So we're going to be demoing and showing you this really sweet API that the engineering team deployed in our 6.8 DSE graph product. And it essentially uses a little bit of intelligence to tell you what the best way to index your graph structures would be. So we're gonna do that.
I got to tell you, okay, so yes, this whole series of what Denise and I are doing, again, I generally have not looked at these notebooks ahead of time, and you're kind of watching the first time experience as Denise brings me through these things. But I've done things with graph, right? And index 4 and the analyze, what we're going to see today, I gotta get excited about this for a moment, because for those of you who've been doing graph up until this point, and if you were using DataStax Enterprise Graph or whatever, the indexing, I think, was probably one of the most challenging things. You would start to figure out all your traversals and everything. But then as you start to then, if you come out of a development mode and you start to execute traversals, you constantly get messages about like, well, you need an index here, you need an index here. You have to go down and figure out what indexes do I need, what material I've used. It was honestly kind of a pain in a big time sink. And when I want to say it was 6.8, right? That came with 6.8?
It did, yeah.
With 6.8, they released this new capability that Denise is talking about, where you can literally just plug in the traversal and say index 4, you wrap it with index 4.analyze, and it goes, oh, here's the indexes you need. Oh, you already have the indexes you need. You're good to go. It is wonderful. Oh, and by the way, if you do have indexes that need to get implemented, then you can just tell it to apply, and it'll apply them for you. I mean, it was like, so yeah, I'm still excited about it, if you can.
Yeah.
Anyway, with that.
Yeah, no, so we DataStax has been taking a big step towards the world of AI ops. And so this really is starting to show you all what it means to have a little bit of an intelligent recommendation service built in as an API call.
Yeah.
So I'm really looking forward to getting to that.
It's totally right. I'm excited.
Yeah, so if we get through all that, I am dying to show you guys where we're going in chapter 6, because chapter 6 is my most favorite chapter. But we'll see if we get there. I gave David a video to kind of preview this really cool blend of time series data in a graph that one of the United States' largest energy companies uses to proactively predict tower failures or different failure scenarios within the power grid. So that's where we're going in chapter 6. And if we have enough time, I'd love to show that video at the end of this session today. If not, we'll kick it off next week with that video.
Cool.
So,
all right. So with that, should I share my screen? Let's do this.
Let's do this. Yeah. So we'll make sure we keep sharing some links. But where we're getting started is we're getting started in Lucidcharts. So we're going to start with diving deeply into understanding how to map an adjacency list, which is just a term for graph data structures, into Cassandra. And for those of you following along, we also open sourced all of the images for our that we used for creating and writing our book. It is available in Lucidcharts, and that is what David is sharing now. I do think that sometimes YouTube strips out my links, but I can post it to LinkedIn here if some of you haven't found your way to the Lucidchart images.
And Denise, if you need to, just post your links in the Slack channel. I'll grab them. I'll put them in YouTube.
Okay, cool.
I guess we need to give you the proper access to the YouTube channel.
Yeah, no worries. I'll post it here. Lucidchart links just came over to you in Slack, so you can post them.
Got it.
And I posted it on. I posted it over on LinkedIn. So
you did. All right. I'll post it in YouTube, and there you go in YouTube.
Awesome. Thanks, guys.
And I see the Lucidcharts in LinkedIn. Wonderful.
Great. Yeah. So what you all are looking at is you're looking at the series of Lucidcharts, the public version that we used, or the public copy that I created. There, as you can see on the tabs there, they're all of the images in our book by figure number there on the bottom. And so today we're going to hang out, I believe, starting over at image 5, 6, I think.
6. Okay. Let's see if I can't. Oh, if I blow it up too much, it's going to be too much. So let me open this up. I think, yeah. Okay,
Yeah,
I do have to. Hopefully, everyone can read this. There we go. I eventually figured it out.
Okay, cool. Yeah, it looks good for me on the screen that I'm sharing. But again, let us know, those of you who are following. Again, if you're watching this live, we have the comments pulled up here on YouTube and on LinkedIn. So if you're following on another source, because I know we're also promoting to other platforms, if you do have questions, if you could post them on either of those two channels, that would be the best way. Best way to make sure that we get in here. Okay, so what are we looking at? We are looking at, David. We're looking at the three different types of data structures that you can use to represent a graph.
Okay.
So the graph that we have as an example is on the top, and the three different data structures are an edge list, an adjacency list, or an adjacency matrix.
Okay.
Now, David, question: have you worked with any of these before?
Not really. I would say the edge list, yes, but not so much the adjacency list and the adjacency matrix. Not as I see it here. Okay.
So what we're doing is we're showing you all of the data structures that you can use for graph structured data in any system. The implementation details under the hood for how we have mapped a graph structure into the distributed system, the distributed table structure of Cassandra is that we're essentially a distributed adjacency list. So Cassandra, when you're using DataStax Enterprise Graph and you're using your partitions to create graph structured data, we're pretty much working with an adjacency list.
Okay.
Just so you know. Oh, and yeah, thanks, Kamal, for confirming that that you can read it. So, for those of you following along, let's just walk through what this is showing. An edge list is going to be a data structure that essentially represents all the edges. So it's going to be all pairs of A to B. An adjacency list is going to be the vertices, like keyed on every vertex, and then a list of adjacent vertices. And the adjacency matrix is going to have a row and column for every vertex in your graph. And then at that IJ pair, if there's an edge, it'll have some information. So let's go through, like, kind of map this data into each of those. So the graph we have at the top is still our financial data. So today is going to be the last day we talk about our financial example where we've got customers who own credit cards, accounts, and loans. And in this example, we have customer 0 who uses credit card 17, loan 32, account 14. Right?
Yeah.
And on the edge list, you can see that the first 3 edges that we have listed there are for customer 0, and then to account 14, that you can see the AB pair, right? You go from customer 0 to account 14, customer 0 to credit card 17, customer 0 to loan, right?
Okay.
So David, I'm curious, can you kind of see or if you had to, like, walk through all of customer 0's edges, right? Mm-hmm. Do you see how it's kind of sorted alphabetically by the second one on disk? Oh,
interesting. Are you talking here about in the AB pairs? It's essentially sorted on the B's, if you will.
Exactly. So now you're starting to talk about how you would index an edge list. If this was the way that your database was working, now you're starting to get into indexing details, right?
So does this edge list translate into a Cassandra table with a clustering column?
It would, except DataStax Graph doesn't use edge lists. It uses adjacency lists.
Okay. So you're starting to tell a story here. I feel a journey coming.
There's a journey. There's always a journey. If we're talking about graph data, there's always going to be a path somewhere.
Right. Okay.
I have a feeling the puns are going to be strong today.
You're very punny, Denise.
Just wanting to make sure that you feel connected, David. It's bad.
For everyone watching, let's dad joke and pun it up. Come on.
Anyways, okay. Yeah, so the way an edge list works is you can imagine now if you're thinking about using this data structure, there's a way to kind of have a sorted entry into the edge list, because you can sort based on the A pair, but now we're bound on how quickly you can sort through an edge list when you're talking about millions and millions of entities, because there's no specific key for an edge list. It's just edge pairs.
I see. Yeah, I get your point. Okay.
And so if you're looking at this saying, it's going to be pretty expensive to scan through all of my edges. I mean, even doing a smart scanning algorithm, you don't have a direct index to say, I want to start at customer 0 and start walking. You're going to have to scan all of your edges until you get to customer 0 and then start walking.
Okay.
So edge lists are the best for space because they are going to minimize the amount of space needed to store the entire graph. But you take a hit then on performance by having to scan through all of your edges before you can start a traversal. But there's trade-offs depending on what you're doing. But from a traversal perspective, that's why edge lists are great for space, but maybe not as great for starting at a specific point and then walking through your graph. Now, there's tons of smart things you can do to change edge lists, but the way we have implemented them were more for adjacency lists. We're going to end on adjacency lists, so let's hold on that and let's go over to adjacency matrices.
Okay.
Adjacency matrices, like we kind of talked about, every vertex is going to be a row and a column. And then if there is an edge for that pair, you're going to have information in the cell. So
I see.
So you can kind of see the same thing, right? For customer 0.
Right. And looking at what we have in our edge list and in our adjacency list, but if we take the first relationship here between having the edge between customer 0 and account 14, right? And I know that that's customer 0 owns account 14. I can see here in the matrix at customer 0, I have a hit on account 14, which is the owns edge. Okay.
Perfect. And now see, for figuring out if there is an edge between customer 0 and say like account 14,
okay,
an adjacency matrix is going to be the fastest way to look that up because you're going to have 2 indexes to directly hit the index of your actual vertex ID, right? So you can index by the row and then index by the column. And you're basically going to have, a constant time lookup of whether or not an edge exists.
Interesting. Okay.
Adjacency matrices, the fastest. So that's why we talk about all the time, by the way. David, we talk about this all the time. Like when your graph is small enough and you're just going to hold it in memory, you don't necessarily need the full implementation details of a database. And that's maybe what's happening with a lot of the libraries who are processing graphs in memory. They're just using a massive adjacency matrix because it's the fastest way to do analysis or lookups of different types of information in your actual graph structure.
I see. So then it's just a way that you can essentially very quickly determine, do I have an edge here between these 2 vertices?
Yep. Not
without having to
quickly,
scan
the
through
fastest.
it. I see. Got it. Okay.
But guess what? I'm sure you can figure out, how do you think space is with adjacency matrices?
Well, given what you've said so far, there's a definite implication here that this is going to use a lot more space.
Absolutely.
Yet it's going to be a lot more efficient.
Yeah, it's extremely sparse. So when you have adjacency matrices, you can see already that you're storing, a minimum Boolean or whether or not an edge exists for every pair of vertices in your graph. So if you have 1 billion vertices, that's a lot of extra, wasted space that you essentially have. And so the kind of the hybrid model is the adjacency list here, where you're going to have direct lookup for an individual vertex, but then you'll have to scan just that individual vertex's edge list in order to find the edge. So it's kind of a hybrid on space and time for looking up and walking through your data.
So the adjacency list is the compromise between the edge lists and the adjacency matrix.
That's how I like to think about them and talk about them and reason about the differences between these 3 structures. So yes, and for practitioners who are really, really deep, there are a ton of different ways that you can implement these if you want to build your own graph structure. And tons of edge cases you can get into. But I want to walk back from all of those super deep details and kind of just stay high level at this point.
Okay.
So can you, for the adjacency list, can you walk me through how we're storing customer 0 in an adjacency list?
Well, it looks like to me that I see this reference to the customer 0 and then an array within it that has all of the edges that do in fact exist, and they are alphabetically ordered.
Yep. And so to your question earlier, what do you think a clustering key might be now in Cassandra?
Well, yeah, the clustering key the clustering column here looks like it is in fact the name of the connected vertice.
Exactly. That's it.
Okay.
That is it. So that's going to be...
I'm glad I got that right. Every time you ask me one of those questions live, I'm always I hope I get this right.
Yeah. And I mean, for those of you listening, David and I don't rehearse this beforehand. So I appreciate your bravery. Just being like, well, we're going to figure this
Someone's
out.
got to do it. Someone's got to do it. Right. Yeah.
Yeah. But no, that's absolutely right. So You do have that, you do have the O of 1 or the constant time hashable way to look up which vertex. And that's the key of your adjacency matrix. Or for those of you who know Cassandra, now we're really starting to talk about the partition key.
Right,
that's going to be the way that you uniquely identify as fast as possible, the individual vertex that you're going to start walking on. And now when you are going through all their edges, that's where you're going to end up getting more time or processing time into your traversal, because you have to scan your full vertex's edge list to see where to go. But we can be smarter. So let's show everyone how we can be smarter.
Ooh, let's do it.
Come on. David, you do know what you're doing. Which sounds terrible the way I just said that live, but this is why we do this, because I know you're a rock star. So anyway, so let's move on to what I think 5.7.
Okay, let's go to 5.7. Boop. You know, I just booped. That's so funny. That's something I do with my little 2-year-old.
Yeah.
I go boop, and I now apparently that's in my lexicography.
I'm okay with it. I think it's good. Okay.
Or for anyone who's old enough and remembers back in grade school, those watching, God, what were the view screens called with the record player, and they play the story, and when you had to turn the page, you go boop. Anyway, sorry.
Yeah, I think we're in the same. Nope, I don't remember that, and I feel like I should be in your audience for knowing that. I mean,
wow.
Or I was playing with too many graphs as a child and just.
I don't know. Yeah, I guess maybe I just kind of outed myself somewhere. Okay, we'll find out.
It's okay. You know, it's fine. Okay, cool. Yeah. So for that last example, what we're looking at here is how you would essentially map and create that distributed adjacency list in Cassandra. And, you know, we're looking at the Cassandra schema and we're looking at the graph schema. So far, this entire time for the first few episodes, we've been looking at graph schema on the bottom, where we talked about customer vertex with a partition key of the customer ID. There's an edge from the customer to the account, and that edge is called owns. And then the account has a partition key, and that's the account ID. So now we're kind of adding in that layer above, which is to show you how this maps into Cassandra. And David, you're the Cassandra expert, by the way. So David has way more Cassandra experience than I do. I'm coming from Graphland. So can you talk us through the Cassandra schema that you can see?
Well, yeah, it looks like to me that for the 3 tables, let's just start with customer. That's going to represent our vertex itself, right?
Yep.
And then, from there, we're going to have some partition key being the customer ID in this case, and then some identifier or some label like the name. I'm going to skip over customer owns account. We're just going to go to the next vertex, which is account on the very right-hand side.
Yep.
And again, you need to have your partition key. We're going by the account ID. I think the key thing that I love this chart, by the way, because this is fun, especially since it does this nice comparison. I think everyone watching will probably be able to see what's going on here. This customer owns account table is essentially our edge, right?
Exactly.
And that primary key in the clustering column we're looking at are the implementation in a Cassandra table of the adjacency list.
Exactly.
That we were just talking about. So we see our primary key with, our partition key against the customer ID, and then that clustering column on the account ID, as you just talked about. What's really cool here is that, just looking at the graphic, you can see the direct correlation between what's going on in the graph schema, what that schema looks like, and then the direct implementation in the Cassandra schema. So honestly, it feels pretty clear looking at what I'm seeing here.
Yeah, exactly. And to your point on the last slide, when I just kind of tossed the softball over your way and you knocked it out of the park, we can see on this first implementation that your clustering key is going to be your in-account ID. And so that is how you are sorting the access to your edges in Cassandra so that it's as fast as possible.
Yes, that's very cool.
Yeah, so I think on the next one, we took the data and mapped it out so that you can look at the data in the table form, but then also in graph form.
Oh, here we go. I always like concrete examples.
Yep. So for one of the examples on that previous slide, or I think on that slide on image 5.6 from the book. So again, for those of you who are following along, we are going through chapter 5 in the Practitioner's Guide to Graph Data, which I have a copy of it on my floor over there. I'll have to go pick it up in a second. And we're just kind of giving you all a deep tour through this actual chapter, and you can get it for free on DataStax. It's a resource. You can download the PDF for chapters 3, 4, and 5, so you can actually follow along with this content. But after this week, we're diving into chapter 6, which is not available for free, but you can absolutely follow along in the code. But what we have here is we're looking at customer 0 and his account. And the graph representation that you're going to see when you're using DataStax Studio and you're developing, you're going to see what's in the bottom. You're going to see a vertex and you're going to see an edge, and it's connected to account 14. But David just walked us through how that's going to map out into Cassandra data. So we've got the 3 tables. You're going to have your customer table where your partition key is your customer ID. You have your owns edge table in the center where your partition key is customer 0. Your clustering column is account 14. And then the final table is going to be the account table where the partition key is account 14. So I think, David, so here's the aha moment, I think, for getting into the next slide. If you were to add an edge, if you were to say that customer 0 is an owner of account 14, but on this next right, we say that their own is secondary, like they're the secondary, their role on that account is the secondary role. Looking at that Cassandra data and your knowledge of Cassandra with what happens with the partition key and clustering columns, what's going to happen to that role property?
It feels like to me, because role, I think, is a data column here, right?
Yeah, role is just a data column. The partitioning key is out customer ID. The clustering key is in account. And then role is just a data column.
So it feels like to me that we just simply have another row in that same customer 0 partition against account 14 that's just it's gonna have a, what'd you say the role was called?
It'll be like secondary. So like when you have bank accounts, yeah.
It would just be, it feels like it would be another row, but the difference would be the role would be secondary, because I'm feeling that the role is an actual edge parameter here, or property is what I'm trying to say.
It is, but with this table implementation, when you go to read customer 0, are you going to read that it has a primary and a secondary role, or are you only going to read that it has a secondary role, which was your most recent write?
Oh, I see.
Yeah.
I think I see what you're getting at. Yeah. Well, with this implementation, I feel like we're going to read both.
Okay. Walk me through how you see that.
Well, let's see. Oh, I guess it depends. If it depends on if you're reading the table. If you're just going for the very last write,
yes,
you could just read the first row depending on how you have things ordered. But I'm not seeing any kind of time series stuff in here at all. So I think I'm missing something, Denise.
Exactly. There is no time series data in that's great.
Okay. Are we going to bring that in now? Is that what we're doing?
Well, we're going to bring something in. So here's what's going on. So because for those of you who have followed Cassandra, when you have your full primary key is your partition key plus your clustering columns, and that determines uniqueness in your table, right?
Right.
So the uniqueness in our table is that there's an edge between customer 0 and account 14.
Right.
So if we go to write a new edge between customer 0 and account 14, it's going to upsert it without some uniqueness. Exactly.
In there, yes.
Exactly. It's going to upsert it, and therefore it's going to change the role to being secondary.
Oh, I see what you're getting at. I understand now. I wasn't following the question correct. If I were to,
I'm sorry.
No. It's yeah. If I were to then update this or write this at customer 0 account 14 with nothing else that was defining any uniqueness for role, it would just upsert it. So primary would essentially get replaced.
Exactly.
Secondary, and it would go away. So that would be bad, I'm assuming.
Well, it just depends on how you want your
depends on the data model, what you're trying to do, right?
Exactly. So typically, though,
I see now.
For some of you who are following along, going, "Wait, what? I didn't quite follow that." Typically, when we think about graph data, you want there to be as many edges as possible between customer 0 and account 14, and you want to represent that they've changed over time or that you have new ways to represent roles. But what I'm showing here is that you also have to really understand Cassandra under the hood. And there's 2 things to really understand here. You have to understand the role of a partition key, and you have to understand the role of a clustering column.
Right.
Your partition key does a few things, but for this context, the partition key is the first part that determines uniqueness. The partition key with the clustering column is considered unique. Like those together define the uniqueness for your edge. Anything after that, you just take the most recent or the last write into the database. But to David's point, he was like, wait a second, like I really want there to be 2 edges. So let's go ahead and flip over to the next image so that we can look at what you have to do with your schema to make sure that you get both of those edges. This is really what you need. So let's start first into the Cassandra world, and then we'll go down to the graph schema. So in the Cassandra world, we still have the same, we still have the same customer table, and we still have the same account table, because
that's cool.
Yeah, our partition keys, that's our full primary key, and we only need to know the customer ID for customers and the account ID for accounts. So that's going to be uniquely how you identify those pieces of data throughout your graph. But now what we want is we want our customer to have as many roles as possible between your customer vertex and your account vertex. And that means we have to bump role up into being a clustering column.
Right.
Yep. And what we want to do is you have to think about how you're going to, you have to think about how you want to traverse this data. Like you might want to say, for this customer, I only want to consider primary, when their role is primary on accounts, and go to all of those accounts. And so that's why role has to be the first clustering column.
Right. I could see that. Yes. Okay.
Yeah. And the way that we represent that in graph schema is what you see at the bottom. We've seen this a few times.
Yeah, we've seen this.
The only difference between these schema drawings was the single line versus the double line.
Right.
So when it's a single line, it's just going to be that we don't have any clustering keys on our edge. But when there's a double line, you're thinking more that I want to represent multiple ways that this customer can be related to this account. And that's what you're doing there.
So that's saying essentially that I can, as far as the owns edge goes, and from what I'm seeing here depicted, that is saying that I could have multiple role relationships between the customer and the accounts.
You've got it.
Okay. Okay.
And you know what? If you don't want to think about all this, Index 4 will help you with this too.
Okay. Cool. And the neat thing too is looking at this table, then now if you notice, since both role and the account ID are clustering columns, all three of these come together to form uniqueness. So I don't have to worry about the upsert problem as well.
Exactly.
So if I were to start with primary and then I wanted to add a secondary, even at the same partition key and the same account ID, that's totally fine, right? I will not have a collision with an upsert in that particular case, and I'll be able to represent multiple rows here.
Yeah. Yeah. So let's go ahead and take a look. I think we're at like 5.9 now, maybe is the next image. Kind of forget what.
Yeah, we're on 5.9.
Yeah, let's take a look at 5.9, and then you'll go to the next one then, 5.10. Sorry.
Oh, okay. I was like, we're at 5.9.
Sorry,
what am I doing wrong? What am I doing wrong?
Not doing anything wrong.
Here we go.
Yeah, so David, this is what you were describing that you wanted to see, right? We wanted to be able to have two edges between Michael and Michael's account. And that's what we see here now. Because we bumped role up to being a clustering column, right. We are now going to have all of these edges, or an edge for every single version of role with that account pairing able to be modeled in the database. So like before, the top is walking through how the data, the distributed adjacency list is mapped out into Cassandra, and the bottom is giving you the graph view. So do you want to walk through the Cassandra data?
Yeah. So again, I think with the customer, the customer ID here, or the customer table, if you will, and then the account tables, these are both just our vertex representations. You know, I was actually going to make a comment about this. And correct me if I'm wrong, but it feels like the vertex representation that I'm seeing from the Cassandra end for our graph schema is extremely simple, right? I mean, yeah, maybe we don't have a lot of extra properties, but even if you had properties, you could identify those in some data columns. But other than that, it's like, here's your IDs. Oh, actually, we do have a property name. Yeah, there it is. But here, here's your ID, and there's your partition key, and good to go, right? So it seems like those are really simple. I feel like any of the, like, say, not that hard of logic, but any more complex logic is where you get into these edge tables. But this feels like this is where the rubber meets the road kind of thing are in these edge tables. And ensuring, but again, as you just talked about, we have our partition key on that customer. We see multiple representations of the same one, but again, since we have clustering columns on both row and account ID, I know that all three of these come together as my primary key to give me uniqueness, right? So each one of these are unique. And again, we see that we have that clustering column on row, and this will allow me, in this case, to have multiple edges that connect over to account 14. Yeah,
and David, what you just said is gold. the rubber does meet the road in these edge tables. And it's a new way to think for everybody, for everyone who's picking up graph database and graph databases and graph technology. Understanding and having to stretch your brain to think about edges first, and to understand the influence of your edges into your database, either be it on disk or into the data structure you're using in memory. It's all about the edges. And that mental shift is really hard for everybody. And I'm really looking forward to feedback or comments or questions that anyone could have. Again, we're following YouTube, we're following LinkedIn. I've had some issues getting LinkedIn comments. So if you guys are commenting on LinkedIn and I'm not seeing them, I'm watching it. It's probably me.
I hope that I'm seeing the latest ones, but I am watching them live, so I haven't seen anything.
Yeah. There's a lot of thought leadership that we've participated in, just discussing at a high level that graph data and graph databases are about this idea of having relationship first thinking. Yeah. And it makes sense at a high level. And all the way down here at this table level, when you're persisting it on disk, is exactly where it comes into play. So if this is the first time that someone following is seeing this, it takes a few times to get used to really understanding how to think in relationships, because for so many years, our brains have been solely focused on thinking about data in silos of just individual tables. And yes, we still are talking about tables here, but the important part is understanding how to connect these tables together across a massive system, how to really think about all of your data as a distributed adjacency list. That's the hard part. And it takes a few times to see it. So if anyone has advice or comments, or this made a lot of sense, let us know. I don't quite really understand where you guys are going with this detail. Let us know, because as a community, we're going to have to figure out a way to make this as easy as possible for everybody. So
I got to ask though, I feel like there's a pattern here that once you've kind of grokked the pattern and gelled it into your mind, that you're probably pretty good to go.
Yeah.
Like, so if I want to extrapolate this, and let's say that we're not talking about just customer account and the edges between those, but then I want to, as we've seen throughout the series so far, we obviously have more vertices, more edges. This feels like this is a little bit of rinse and repeat, as in if I want to then create another vertice with another edge or set of edges, if you will, then I could probably apply something very similar to that as well. So is that true? Like, are there like just a finite number, a small number of patterns that once you kind of understand those, you can just kind of rock and get going with your schema? Is that true?
That's true. And like perfectly tees up exactly how my brain looks at this whole world. You should be scared, David. You're starting to, I don't know.
I think the graph databases out there should be scared.
No, but no, to your point, David, exactly. There are a common set of patterns that people have just organically started creating for these implementations. And we are, 5 episodes into deeply studying the first most common pattern. And it's what we call customer 360. And it's where you're solely concerned about your customer and neighborhoods of data connected to your customer. So most of your queries are about this customer, tell me something in this first neighborhood, or tell me their account information.
Oh, so the patterns themselves are actually tied to the type of use case.
Exactly. Yes, they are.
That's actually kind of cool. That's pretty cool, because like for those folks out there who because one of the questions we always get, right, is when we've done some of our developer days and other things like that with Graph, and inevitably you get questions. Well, I've got this use case and this use case. How do I even start? And now what I just think I heard was, okay, well, maybe you have a customer 360 case. Maybe you have a recommendation case, whatever that is. You can kind of like use these as boilerplate to, here's your starting point. Here are the patterns you need to look at to handle that kind of use case.
Exactly. Cool. And that's what chapters 3, 4, and 5 are all about, right? It's all about understanding, can you just show me exactly all the way through end to end how to model my data, how to insert my data, how to query my data, so that we can do this. And we've spent a lot of time with querying. We just went through and did some deep dives on kind of understanding how it gets modeled into Cassandra. So maybe we should do some loading.
Let's do it. Let's do it.
Okay.
Let's do it.
What? Yeah. Where are you in your setup, actually?
Okay, so I have, I should just explain that real fast. I don't expect everybody to be able to read what I just did, right? But I have one DataStax desktop. If you remember that from last week, we used it last week to start up the graph book repository. Now, just to be clear, this is the same repository and everything that's coming out of this, right? That Docker image that we have here. The only difference is that in DataStax desktop now we've exposed. I can't remember. By the way, I can't remember if this is the beta version that's actually not out yet, or if it's the one that's out.
It is. It's the alpha internal release that we're previewing for everyone here. And as soon as the engineering team is working quickly to cut this as the next data.
So this will be coming out soon in DataStax desktop. But what it really comes down to is I'm able to go to the desktop, go here, and just launch the GraphBook examples. That's what we're looking at now. Then that in my Docker has loaded both Studio and DSC with Graph enabled. So that's all ready to go. Now, with that, clear this out. What I've done here locally is I have taken,
Can you maybe make that just a little larger?
Oh, does it need to be bigger?
I do. Yeah, I do think so.
Okay,
no worries. I missed that earlier.
How's that?
Maybe one more.
Okay. By the way, while I'm doing that, there's a question, Denise.
I do see that, yeah.
Do you see that one?
I do. Great question. So question just came over on YouTube. For those of you kind of wondering where we're taking questions, we're following YouTube and we're following LinkedIn. Is there a limit to the number of edges between two vertices beyond which it impacts the performance? So that's a fantastic question. And the mention of performance essentially is going to be where you first hit any type of impact. For processing, millions of edges in the middle of a traversal or any algorithm, just adds a lot of time. But on disk, there technically is a hard limit that you're going to reach on disk. And if I can try and reverse engineer the math that we wrote about, we walk through this in the book so that you have all the exact math. And the book is available for free on DataStax at DataStax Resources, the O'Reilly Graph Book Guide. So you can download this and read all of these details. But the simplest edge design would be your partition key is your outgoing vertex. Then maybe you have like a clustering column that's a timestamp. And then you have another clustering column and that's your incoming vertex. So that's going to be your simplest design. That's 3 columns in your table. And if you go through the math of how much space that takes up in Cassandra on disk, I think you hit a limit at like 6,600 billion or 666 billion, 666,666. It's quite an evil number.
I feel like I need to have a voice changer. Like,
Yeah. So when you map out, depending on your data types, right? Because a 32-bit integer is going to take up less space than a 64-bit integer.
Right.
But I believe we did this for 64-bit ints. And how much those 3 columns would take up on disk, and like when would you actually hit an overflow error on disk? Right. And it's 666 billion, 666,666, and so that would be the actual hard limit. If you added one more, once you got to 667, you would hit an out of memory or out of bounds error with the number of edges on disk. But that's all laid out in chapter 5. If those of you listening want to actually walk through the math and see it in detail, download the PDF and read chapter 5. It's there. But to the question, you're going to hit performance issues way before that. So it's going to be more about understanding supernodes, understanding branching factor,
right,
and understanding what's happening in your traversal well before it's going to have any issues on disk. So
is that some of the stuff we're going to get into as we go further on down the series?
Yes, it is.
Oh, what do you know? Well, thank you for the question, Maha. You're kind of pointing us to where we're headed.
Yep. So I think so. Great question. So for data loading here, I think do you have everything cleared out and we're just loading vertices and edges?
Yeah. Okay. So like I said, I've got the Docker image loaded with all the stuff. We did drop the schema beforehand. Now, this is what I want to point out is, as you saw me going back, clearing and print working directory over and over and over, because every time I'd zoom, it would reprint everything on the screen. All I've done is I've just pulled down the graph book repository from GitHub. That's it, right? So you see the directories here. Now I'm just doing what the instructions in the repo tell me to do, right? We're working with chapter 5, so I'm going to go to chapter 5, and you'll see this chapter 5 load shell script, right? So if I take a look at that, and again, I'm just showing you what it actually has and what I did. So you notice what I've commented out here, this first line. This is the default. You'll see in the instructions as well, it'll tell you, hey, you need to change this to wherever dsbulk is. So the instructions also do explain to you where to get dsbulk and how to download it. You'll see that I have downloaded it here. I've got it in a directory. So dsbulk is a tool that you can use for both open source Apache Cassandra and DataStax Enterprise. It's like the standard way to load data into the system. So we're going to use that here. So I've essentially installed dsbulk, and I've pointed my default dsbulk path to the path of where that is. That's it. I changed that one thing, right? And then from here, all I have to do is do this. I'm now going to load the data that's coming from all of these different CSVs, right? You'll see as it goes through, there it goes, right? It's going to start giving me some data on this, and it's going to start to load all this data into our graph.
Yep. And yeah, exactly. And so what we can do once that, so this is the notebook where you can run all the traversals for chapter 5, and we can start showing index 4. I'm wondering if, because I don't want to quit that data load, is there a separate window where we could look at one of the data files, or we can always wait too?
Oh yeah, I have it right here. Is this what you're looking for?
Perfect. Yeah. Let's go ahead and just open up one of the Vertex CSVs, like transactions. Perfect. So what we're looking at here is we're just looking at the data file that is being loaded by dsbulk, and we're looking at an example of a Vertex table. So we saw in our schema on some of the previous examples that our transactions had an ID, they have a timestamp, and then they have a transaction type. So you can see that this is exactly loading the data directly into the Vertex table in Cassandra. And for those of you who are wanting, potentially to know the trick of the day with this, you want to make sure that your header line at the top matches the schema name in Studio or in your actual Cassandra schema. Yep, those have to match exactly the name of your database schema elements.
I'm curious then, if we were to scroll down, we're creating in our schema, we're creating transaction. We have transaction ID, transaction type, timestamp, and if I go back here, transaction ID, transaction type, and timestamp. And they need to be the same, right? I see transaction underscore ID, transaction underscore type. So, okay, so that's what you're talking about, that mapping?
Exactly, yes, that mapping has to be exact. Yep.
Okay.
Let's take a look at an edge file, because those have a different mapping that some of you guys might not expect.
Okay. How about owns or O's?
Yeah, owns or O's would work.
Okay.
So the name of the file doesn't matter. What is super important, though, is that we understand that header line. So in owns edge that we've looked at, we know that we're going to have a partition key, that's the customer ID. We are going to have a clustering column that's role, and then a clustering column that's the account ID. Now, the order of them in your CSV does not matter. So that's why they're in a different order here. So don't be concerned about the order of the columns. It's the name.
Yeah, you can configure that from dsbulk to handle that part.
Yeah, you can. But I bet you that the name doesn't, that was unexpected. How it's
yes.
Yeah, so let's go over to Studio.
Yeah, I want to see these. Let's see, which one did I pick?
I think we picked owns, right?
Owns. So let's take a look again. Yeah, owns. We're on owns. Yes, so this one.
Yep. So even in the schema, when we named it, I mean, we can do a custom mapping in dsbulk, but like, where did I come up with these crazy column names?
That's a good question. I was going to ask you the same thing, because here it looks very clear, right? But then, obviously there's more going on to this.
There is.
This looks like this is the mapping between what the name in the edge and the name in the vertex are. Exactly.
That's exactly it. So the DataStax engineering team, let me explain two things. If you want to custom name your tables, you can. We've got API docs to show you how to custom configure all these names. But if you just want to say, hey, I want to keep it super simple, make my edge labels and follow default naming conventions, that's what's happening here. And you can get that really easily by understanding how it's named, which is exactly what David just said. It's the customer, it's the vertex label underscore the key. And then the second one here is the account vertex label underscore its partition key.
Right. And at this point, and again, correct me if I'm wrong, but at this point, by the time you're even creating your edges, you should know what your vertices are and have those generated. So you should know what these are. It's not just some arbitrary value or something like that.
You can get it from Studio too. So you remember how you always pull up that table view on the side of Studio when you're inspecting schema?
Mm-hmm.
If you're questioning what it is, we can go right over there. So you go to schema, and we're going to look at the table view, like click on an edge, for example.
Oh, I'm sorry. Yeah, I'm trying to find owns.
There you go.
Here we go.
Yeah, and so in that table view up at the top.
Sorry. There we go. I was having click.
Are you happy?
I'm sorry. No, I'm just having a click moment here. All right, please continue.
No, it's okay. It's okay.
Oh, that was funny.
Yeah, so for customer owns account there, if you click down and there you go, there's the names. So you can see them right there. So you don't have to.
Right. So when you go to create your data, you can just use this as reference if you don't want to have to memorize the pattern. But it's a simple pattern, right? So and again, that's rinse and repeat. Once you've done this once, you're going to do it the same way for all of them.
Yeah. Yeah.
Okay.
So that's what's happening with the header files there. So let's go back and check and see if that data load. Well, I know the data load finished.
Yeah, I popped over there for a moment. This is finished. So we've got all of our data again from all of the CSVs that are here.
Awesome.
Okay.
Great. Yeah. So that's the secret sauce, David, on how to understand the headers for using DS bulk. Because again, we're using the exact same Cassandra tools, and here it is. Here's the most exciting feature out there. It's our intelligent index recommendation system. There it is, folks. So right there, it's called Index 4, and this is how you use it. So over the past 3 weeks or so, we have been developing these queries in development mode. And we've been developing queries that ask questions that walk through multiple neighborhoods of data. So if you missed us walking through all those neighborhoods of data, I recommend watching video 3 and 4, because we do a lot of gremlin exploration to show you how we got to the query that's on lines 1 through 7 here. But what you can do is you put that query into index 4, and you can do 2 things. And I think, David, you were talking about this earlier, right? With the difference between analyze and apply.
Yes.
Yeah, so what analyze is going to do is analyze is going to look at this full query, and it's going to figure out if you need any additional indexes to run that query in production. So let's go ahead and just run it and see what we get.
Ooh. Okay, so it looks like I have a couple indexes that I need here.
Yep.
Now, something I really want to point out, right? Again, I was kind of alluding to this earlier with using this new functionality and how much time and frustration it can save you when you are creating your graph. I just take a look at this.
Yeah.
And think about having to figure that one out on your own, right? Is it doable? Yes. Is it the easiest thing in the world? No. Is there, for people who are really, really well-versed in it, know how to do it, can they knock these out? Of course. But it takes a lot of knowledge to get to that point. And that's one of the things that just had got me so excited. This also, notice these are materialized views, right? There are multiple different types of indexes that you can use, right, with graph. And one of the questions that always came up was, well, which one do you use? Yeah. Right. And that's another thing the analyze does for you. That's why I just get so excited about it. Cause like, it was totally like one of those facepalm moments when I first learned about it, when it was first coming out and I first got to use it. And I was like, oh, wow. It was just, a wow moment.
It's an awesome tool. So if instead of had analyze, you just changed analyze to apply, it's actually going to implement those.
Do you want me to do that?
Yeah, go ahead. Change it to apply. And it's going to take your same query, and it's going to go ahead and implement both of those materialized views, which is going to take a second because we've already loaded some data. It's creating some new materialized views. There you go.
Yeah, and so it's done it. So if I rerun and analyze, it should say I don't need anything, right?
It should. Let's see what happens. Live demos.
Boom. Yeah, that's cool. That is so cool. And that again, I can't say that enough. How cool that is, especially once you start to get a much bigger schema and a more complex schema, and you have all these options, right? It could in the past it was really daunting to figure out like which exact indexes you needed. This is wow. That's
yeah. So for those of you following along, here's the recommendation that we have for what to do here. If you've been following along the past few weeks, we have been working with what is called the dev traversal source. It's when you're starting all of your graph traversals with dev.v and you do your normal gremlin traversal. When you're using the dev traversal source, we're allowing you to walk through your graph without an index. It's like an index-free tool. Yeah. However, there's some guardrails. We're not going to allow you to use the dev traversal source in an actual distributed cluster or in production. The only traversal source you can use is g.v. Right. Otherwise, some guardrails are going to give you some errors and not let you use it. So that's the only change. We're using all the exact same queries we did from the development mode, but now we're showing you how to figure out what indexes you need.
So in the development mode, this would be like that. Is it actually dev.v?
Dev.v.has. Yep. So all you're replacing is g. Yeah.
There we go. Yep.
Perfect. So for those of you who are exploring the notebooks, when you look at the development mode notebooks, everything is in dev. Because it's allowing you to walk through your graph index free. And the production version of the notebooks walk through all the production details for building indexes and making sure you have your keys set to be running this properly in production.
Cool. Okay.
Cool. So David, I wonder if I could, at the last few minutes here, kind of show an example of why we need a materialized view. And I think it's going to be best done back in the Lucidcharts, actually.
Oh, okay. Let's go back to Lucidchart and I'll pull out of this. Which one am I going to?
Let's go to this one, actually. This is exactly the one. So the query we were just looking at actually was trying to say in one part of the query, it's going from customer. It's going from account in to customer.
Okay.
So in order to be able to walk through graph data, do you see it? What was that?
I think so, but I want you to please continue. I think I know exactly what you're going to say. And I'm so curious.
Okay, great. So the reason you need a materialized view is because whenever you're walking through your graph data, you need to know the partition key and the clustering column as you walk through your edges. And there's a moment when you're on an account and you need to walk in to your customer. And you need to know this exact table in flip. You need it to be Yes, you need it to be the in account ID is the partition key. Then you need the role as the clustering column. And then you need the out customer ID as the final clustering column, because you need to walk this edge table in both directions.
So are you essentially then using the materialized view to use the same underlying Cassandra table data model, the same implementation, but using the view to essentially change what that primary key is going to be, instead of creating another denormalized set of tables that represent the edge going the other way?
Yes.
That's cool.
That's the big aha moment of chapter 5.
Yeah.
When you need to walk through and walk an edge in one direction and walk it in reverse, you need that edge table to be represented on disk in both directions so that you have the keys in each direction.
I see that. Yeah. Okay.
Is that what you were thinking when you did the aha?
Well, yeah. The second you mentioned materialized view and then you mentioned directionality, it dawned on me that, I need to go the other way. How am I going to do that without creating, materialized view? That would be a way to do it.
Yeah. Awesome. That's it.
That's awesome.
That's the big aha moment of chapter 5. Wow.
That is so much simpler than the way it used to be.
It is.
I mean, I know we're not done with the different types of indexes and everything, but that is significantly simpler. By the way, we have a question that just came in LinkedIn.
Okay, great.
I don't know if you saw it.
I do.
Oh, you do see it. Wonderful.
I do see it. This is a great question. So Chandran asked, indexes could affect the performance of the underlying Cassandra database. Is there a limit on the number of indexes that we can create? So that's a fantastic question. The limit, I do believe, resides in the number of tables that we have the ability to store on disk in Cassandra. So David, do you know if we've had any additional limits created on how many tables we can store in Cassandra?
I do not.
Okay. The last I heard was 200, but it sounds like we might want to get that confirmed before we put that out there.
Yeah, I don't know if that's changed to my knowledge, yeah.
Yeah, so as far as indexes go, yes, indexes do affect the performance, because what's happening when you use this index is, instead of your database doing a dual write for this edge, instead of your application writing the edge from customer to account and doing a second asynchronous write from account to customer, we're just handling that for you with the materialized view. We're allowing both of those writes to happen so that your application just writes one edge and we handle all of the views of it in the background. The only limit you're going to hit there is going to be the limit for replicating data across data centers, which I think our longest latency is going to be from South America to China or to Asia East. I believe that's the longest latency. It's a few hundred milliseconds. So there's going to be, depending on where your data centers are set up in the world, that's the type of latency you're talking about, a few hundred milliseconds. And in addition to performance, it's going to be the number of tables you can have in Cassandra. So the recommendation here is that absolutely explore your graph data in development mode and iron out your queries, and make sure that when you're moving a query into production, you're only implementing the indexes required for that query. And in this sense, we're really just talking about the number of materialized views needed for your edges.
And that kind of leads into a question here from Maha over in YouTube,
okay.
Which is index creation just as fast and successful when a new index needs to be created for a relatively large graph? So what happens if you already have a whole huge set of data in your graph and now you need to create an index?
That's a great question, and I have a recommendation for that. Actually, David, bonus, if you could show Lucidchart, bonus, I have so many Lucidcharts for all of these. Chandran, by the way, let me know if that answered your question, because I think we're moving on to another one, but let's make sure that one is answered. I think the question, I think you want to go to 518.
Okay, and I just saw a thumbs up. I don't know if that was Chandran, but I saw a thumbs up come when you mentioned that. So
yeah, but to directly answer Maha's question here, when it comes to needing materialized views or needing indexes on graph data, I have a very, very strong recommendation, and that is going to be to load all of your data and then index it. If you have your indexes already turned on and load, you're going to see significant latencies on load because you're going to be loading and adding all of those extra views during the loading process. Now, time just doesn't go away. You just move where that time happens. Load all of your data. That's going to be super fast, and then turn your indexes on. And I believe that's tip. There's one of the tips in here. Load your data, then turn on your indexes. So, okay, great.
Yep, there it is. Tip 9.
Tip 9. Yeah, sorry. The view I have for reading those are not as clear, so it's hard. But yeah, great question. Chandran said that answered the question. Awesome. Thank you for the question. Maha, hopefully the tip number 9 here answered your question about indexing. And for those of you who are following along, we provided a Lucidchart link to all of these documents. And what you're looking at is you're looking at our first 10 data modeling tips from chapter 4 and 5 together in one list. That's figure 518 in our book. It's also figure 518 here in the Lucidchart diagram that I'm going to repost on LinkedIn. And David will have to repost for me on YouTube, as I don't have permissions for that. But yeah, so you'll find all of that in chapters 3, 4, and 5, all of these data modeling tips and best practices. You can get access to 3, 4, and 5 for free on DataStax. We have it as a resource that you can download a PDF. And there also is a way to get free access to this book online with O'Reilly. We have a code that we'll follow up with and post on YouTube and LinkedIn as well if you want the book for free for 30 days on O'Reilly's platform.
Wonderful. And okay, so we are at time.
Oh,
but there is
my gosh.
one other question. There is one question I see is from Jimmy. I think you can knock this one out real fast. Which visualization tool can we use to publish knowledge graph to users?
That's a great question. If you're using DataStax Enterprise Graph, visualization tool for development is going to be Studio. So I recommend,
that's what you see here.
Mm-hmm. You'll have the schema view on one side, and then there's going to be plenty of views of your actual graph data in your notebook view. I just don't think we have any of those queued up in here for chapter 5. So I would recommend using DataStax Studio for, I don't remember. I know we have tons, actually. If you want to load up chapter 8's notebook, you'll see one in there.
Oh, really?
Yeah, chapter 8's notebook has one. So yeah, we'll give you a quick view into the data visualization in chapter 8. And it should be communities of trust. It's coming up. Oh, it looks like they're all clear, isn't it? Yeah.
Well,
okay. Yeah, we used to have them already loaded with the.
Oh, I see what you mean. They were preloaded. I get it. Okay.
Yeah, no worries. We're trying to do stuff live, and it's not actually loaded up. But in DataStax Studio, there is a way to look at your graph data actually as a graph. And otherwise, outside of that, we have a wonderful team of like partners that we use. Oh, look, I think you're calculating a layout for us here. So we've got data visualization partners that we work with, like Linkurious and others, where people build their custom application using using those tools, et cetera. So I think this was a big one that you were looking at.
It is. I realized I'm looking at the traversal.
No worries. Yeah.
Yeah, here you go. It gives you an idea.
There you go. Yeah. So we just jumped into chapter 8. This chapter 8 and chapter 9 show the common pattern of doing pathfinding in graphs. And we talk about this in context of Bitcoin, whether or not you trust the wallets. So that's coming up in chapter 8 and 9.
Cool.
But before we get to that, in chapter 6 and 7, we're going to be taking a tour of time series data in the power grid in the United States. So that's where we're going next. So
wonderful. All right. So with that, we are a little bit over time. Thank you, everybody, for sticking with us throughout the whole episode today. And I can't tell if I've actually come off my screen share because I clicked the thing. Can you see me? Oh, okay. Well, I can't see the interface, so I can't tell what we're doing. But anyway, thank you everybody so much for joining us again today. We hope you got something out of it. I know I did, because every time we go through one of these, Denise is schooling me on all sorts of new information. And this has been very enlightening so far. Thank you again, Denise, for bringing all of us, bringing all of us through chapter 5 here. And so it seems like next week we're probably going to be continuing some chapter 5 work. Is that true?
No, I think we're ready to go. Let's just move on to chapter 6. New use case, new examples. Let's talk about time series data and how you can use graph structures to be proactive in failure scenarios. I've given this talk a few different places around the world. It's one of my favorite examples. So I'm excited to go there next week.
Okay, awesome. And as always, if you have any other follow-up questions or anything, always you can reach out to us on LinkedIn. You can reach out to us on the various chats, and we will do our best to reach out and get you some answers. So with that, everyone, take care. See you, Denise. See everybody.
Stay connected.
We'll see you next week. Oh my God. Stay connected. We'll see you next week.